So welcome to the lecture on design of slab. So the question that is with us is to design a simply supported slab of a corridor of a hospital. So here hospital has been given just to inform that this is a public building. Accordingly we will take the live load on the building, that is as per IS 875. And as you can see in the picture, which is hypothetical, and it has nothing to do with the question, and it is just a illustration that a slab is having two lengths. One, the longer side, it is denoted as Ly, and the shorter side is denoted by Lx, and it is given as 2.5 meter. So as we know that if the ratio of longer to the shorter span is greater than 2, which is in this case 5.5 divided by 2.5, it is greater than 2, slab would be designed as a one-way slab. And one more thing is given in the question, that the slab is supported on a beam which is 230 millimeter wide. I have written as step 0 is to write down all the data that is given. So since it is a one-way slab, we will consider it to be Lx, that is the shorter span, and the value is 2.5, and Ls, that is the width of the support on which the slab would be resting. It is 230 millimeter, and the grade of concrete that we will use is M20. So on the right side you can see that the grade of concrete as per IS 456, minimum grade of concrete that is recommended for mild environmental exposure is M20. So that is the consideration that we are putting here, to consider the grade of concrete as M20. And grade of steel HYSD, that means high yield strength deformed bar of, normally you will find steel in these grades FE 250, 415, 500. Beyond this it is also available, 550 and all, it is available. The first thing that we should have is a trial depth, and as per the codal provision 23.2 that is given in page 37, the span by depth ratio should not be more than 20, right? And there are other factors also, Kc and Kt. There are two factors that we will calculate at the end of this lecture, but for now let us assume that the overall depth be 120, effective cover is 20, which is sufficient for a mild exposure condition for a slab. 20 mm is fair enough. So the effective depth would be capital D, that is overall depth minus effective cover, and it will be equal to 100 millimeter. In one-way slab, how we design, or in case any slab, how we design, we consider it as a beam of unit width, that is 1 meter. The effective span as per codal provision 22.2, if simply supported, not built integrally. This means that the considering that it is simply supported, so the effective span would be clear span plus effective depth, right? So clear span is already given 2.5, and effective depth is, we have assumed as 0.1 meter, so it is 2.6, and center to center of the support, so the clear span is 2.5 meter, length of support is 230 millimeter. So the center to center distance from here to here, it will be 2.5 plus 0.23 by 2 plus 0.23 by 2, it works out to be 2.5, 2.73. So what is the criteria? What the effective span would be the lesser of the two, so our effective span would be 2.6. Load calculation. The unit weight of any RCC member is 25 kilonewton per meter cube. We'll divide it with the cross sectional area, overall depth and width. So 25 B into D, it will give us load per unit length. That is what we are expecting, right? So we have the formula for UDL, that is load per meter length. We will multiply the unit weight with the cross sectional area, so it comes out to be 3. So live load as per IS 875, it is something between 3 to 5. So since it is a public building, we should consider the live load on a higher side, so we are considering it as 5 kilonewton per meter square. So width of the slab is 1 meter, so I multiplied this with 1. So again the unit changed from kilonewton per meter square to kilonewton per meter. So the total working load, that is dead load plus live load, is equal to 3 plus 5, 8. Now since this is a limit state method and we use the factored load, which we call as the design load, and we multiply with the load factor, that is as per IS code. So simply multiply this total load with 1.5, that is the load factor. The total design load would be 12 kilonewton per meter. Okay, so the maximum bending moment for a simply supported beam would be WL effective WL square by 8. So we have reduced the load in the form of UDL. Now the maximum bending moment would be 10.14 kilonewton meter, and shear force is nothing but the reaction, that is 15 kilonewton. Then the effective depth required. At the start we assumed a trial depth as equal to 100 millimeter. Now we'll check whether it is sufficient or not. So for that, what we do, we'll equate the value of mu that we calculated in the previous slide and equate it with the value of mu lim given in IS code page 96. This formula is given. Instead of using this long formula, you can directly refer to this simplified formula. And for FE415, the value would be XU max value is 0.48D and the value is 0.138 FCK BD square. So the value of mu that we calculated in the last slide simply equate with 0.138 FCK BD square. FCK value is M20, so 20 it would be, and width for a slab is always 1 meter. So when we solve this, when we equate this, we will get the value of D as 60 millimeter. So the required depth is 60 millimeter and trial depth is 100 millimeter. So that is fair enough. What is required is only 60 millimeter, but we are offering 100 millimeter, so this is same. So good to move ahead. Now the next step is area of steel. For this we will equate the value of mu that we calculated equal to mu. Again, this value of mu is given in the code. So when we equate this, we will get a quadratic equation in AST. We will get a quadratic equation in AST. All the values are given: 0.87 Fy. Fy is 415, AST is unknown, D we assumed it to be trial depth is equal to 100. Again, AST is unknown, B would be 1 meter, that is 1000 millimeter, D is 100 millimeter, FCK is M20, that is 20, and Fy would be 415. So AST is equal to 300 millimeter square. Now in limit state method, we need to check whether the value that we have obtained is within the limits or not. So this value we have to cross check against the minimum and maximum value. From the codal provision, the minimum reinforcement is provided to resist creep, shrinkage, thermal and other environmental requirements irrespective of the structural requirement, because structural requirement would be from the strength perspective, right? So whatever load is coming, based on that the requirement of steel is 300 as we saw, but minimum steel requirement is provided to consider the other aspects such as creep, shrinkage, thermal and other environmental requirement. So as per code, this again it is given in IS code 26.5.2.1. you will see that for mild steel the value is 0.15% of total cross sectional area, that is B into capital D. Overall depth you will need to consider here, and for HYSD, as in our case we are using FE415, so this is 0.12% of BD. The minimum will be 0.12% of the cross sectional area, 0.12 by 100 into width is 1000 millimeter and overall depth is 120 millimeter. So from there we can calculate the minimum. The maximum value is 4%, that is 0.04 B into capital D. Again this is given in IS code. In limit state method we will provide the steel that is not less than the minimum and it is not more than maximum. Criteria for maximum reinforcement, it actually depends upon because if the percentage of steel in a cross section is more than the maximum, it will cause congestion in the reinforcement and the concreting would not take place properly, right? So because of that we are restricting the value as 0.04 BD. So AST required is 300 millimeter. So what are the various sizes that are available in the market? We will try dia of bar as 8 mm and the cross section area of one bar is 50. So generally we take it as 50 and actual value is 50.3 pi by 4 dia. In case of beam we will calculate the number of bars, but here since it is a slab we will calculate the spacing. So spacing, the formula is B into A5 divided by AST. B is 1000 millimeter again. A5 is the area of one bar. So it is pi by 4 into 8 square. So it works out to be 50.3. And what is the area of steel? It is 300. So S is equal to, it is around 167. Again we have calculated a value, that is spacing. So we need to check whether this is within the limits or not. Right, so minimum and maximum value we need to cross check. So what is the criteria? So the spacing criteria is given here. The maximum horizontal distance between parallel main reinforcement bar shall be lesser of the two, 3 times the effective depth or 300 millimeter, whichever is less. Minimum value we generally take as 100 millimeters, because again if the reinforcement bar are very close to each other, then concreting, compaction, so we are restricting the minimum value. So generally we take 100. The maximum value is 3D or 300 millimeter. So the spacing would be 167. So let us round it off 160 millimeter. You can take 165 millimeter as well, but here we are taking as 160 millimeter. So hence we are providing 8 mm dia HYSD bar FE415 at the rate of 160 millimeter center to center, that is spacing. The actual AST provided will be, it will be slightly higher than this, because for 300 millimeter square area you need to have spacing as 167. Now we have slightly reduced the spacing, so the actual AST provided would be slightly higher than this. So again what we'll do, we'll use the same equation, then we will calculate the what is the area of steel that is provided. It is 314 millimeter square. Secondary bars or distribution bars, which is generally used for temperature and shrinkage, shall be lesser of the two, that is 5 times D or 450 millimeter. So here for main bars it is 3D or 300, for secondary or distribution bar it is 5D or 450. And for the maximum size or the dia of the bar that we can use for a slab, the codal provision is given as it should be not more than 1/8 of the total depth. So here the total depth is 120. So 120 by 8, with that you can calculate the maximum dia of bar that you can use. But here we are using well under that, it is 8 mm, since the area of steel required is very less, 300 millimeter square. So moving ahead, now let us see that, so this is the diagram that we have. It is not exact to the scale, but just for illustration I have used this. So since the area of steel required corresponding to maximum bending moment, so this is a simply supported slab though, so in that case the maximum bending moment would be at the center mid span, but as we move towards the support, the value of bending moment will continuously reduces. So what we can do, we can bend up half of the bars. So alternate bars from left side will bend up and half the bars will be continuing to the support. And likewise on the right hand side, what we'll do, the bar which were not bent will be bent on the right hand side. So alternate bars would be again bent on the right hand side as well. At the support, the tension steel would be half only. At what distance we generally bend this bar? So it is L effective by 7 minus length of support by 2. So from the center of the support, this distance is going to be L effective by 7 minus LS by 2. LS value is given as 230, that is given in question only. So this value, from where you will bend up the bars, it is actually from the face of the support, it is at a distance L by 7. Okay. So now we know that some 50% of the bars is bent up. So the area of steel at the support would be half only. So the area of steel provided is 314 by 2, 314. So half of it would be 157, right? And it is still more than minimum, AST minimum, right? So let us move. Now we'll calculate the area of distribution steel, right? So this is not to be designed, it is only minimum steel has to be provided. Minimum steel is for HYSD bar, it is 0.12%, means 0.12 divided by 100 into gross cross-sectional area, B into capital D. So it comes out to be 144. Since we cannot use bar less than 6 mm, so this is the least size of bar that we can use for structural steel. So the cross-sectional area would be pi by 4, 6 square. So it works out to be 28.3. So the spacing would be B A5 divided by AST. B is 1000, A5 is 28.3, AST is 144. So the spacing works out to be 196.7. So again you can cross check whether this spacing is more than minimum and less than the maximum value. So the criteria for maximum spacing for distribution steel or secondary bars, it is 5 times the effective dia or 450 millimeter, whichever is less, right? And these secondary bars are essentially provided for temperature and shrinkage. So hence we can write like this: provide 6 mm dia HYSD 415 bars at the rate 190 millimeter center to center along longer direction, along the longer direction. So now the next step is check for shear. Generally slabs are safe against shear, but still we need to check it, because any flexure member we design it to resist bending and we check it against shear and deflection. So as per table 19 clause 40.2 in IS 456, the value of K factor that we need to multiply it with tau c, it is given here. So as the depth of the slab increases, you will see that the K value, that is the multiplicative factor, is reducing. So in our case, what is the value? In our case, the overall depth is 120 millimeter, so it is less than 150. So what K factor we can use? We can use K factor as 1.3. So as I told that thin slab therefore have more shear strength than the thicker slab. It is normal practice to choose the depth of the slab so that the concrete can resist the shear without any stirrup. So idea is to have a least value of thickness of slab so that stirrups are need not to be designed. So let us see what is the check for shear. The selection of depth should be made for normal floor roof slabs to avoid stirrups. However, deck slabs, culvert, bridges, flyover, shear reinforcement should be provided. So these things we would be designing in 8th semester. So it is essential to check the depth of the slab to resist shear. So again there are two parameters. One is tau v, the other is K times tau c. So shear stress and the other word is shear strength. So the nominal shear stress, that is tau v, it is caused by the load that is being acted on the one-way slab. So it is tau v is equal to Vu by Bd. So this value Vu we calculated in the first slide as in the load calculation, it is 15 kilonewton. B as usual, it is 1 meter, it would be taken as 1000 millimeter. Effective depth is 100 millimeter. So the value of nominal shear stress tau v is 0.15 Newton per millimeter square. It is 0.15 Newton per millimeter square. And on the other side, we need to calculate the design strength of the concrete to resist the shear. So this value is K times tau c. Tau c value depends upon the percentage of steel reinforcement, grade of concrete and the multiplicative factor K, right? And if required this check fails, we have to redesign again. So let us see whether design strength is more than the shear that is being acted upon. So this is the table number 19, it is given in IS code. What we'll do, we'll calculate the area of steel. Percentage of steel is equal to 100 into AS divided by the effective cross-sectional area. So area of steel is 50% of 314. So it is 50% is 157. So 157 divided by 1000 into 100. So it comes out to be 0.15%. So here we will see that the grade of concrete is M20 and percentage of steel is either less than or equal to 0.15. So we can directly take the value as 0.28. So tau c comes out to be 0.28 Newton per millimeter square. Overall depth is 120. So the value of K is 1.3. So the design shear strength of concrete means the strength, the capacity of the concrete is 1.3 times 0.28. So it comes out to be 0.36. Value of tau v was 0.15. So the shear attack is 0.15 and the section has capacity to resist 0.36, almost double. So this is again the check is safe. Now we'll come to step number 5. We'll check the deflection as in the beginning we assumed a depth by using this value only. Span by depth is equal to 20, and here two parameters are there, Kc and Kt. Since there is no compression reinforcement, so no point of using this Kc. We need to calculate the value of Kt, and for this we have this figure number 4 that is given in the code, and refer to this figure. On the y-axis we will see the modification factor, that is Kt, that we are calculating using this figure. On the x-axis is the percentage of tension reinforcement. So the percentage of tension reinforcement is 100 AST by BD, so it is 0.31. The total percentage of steel we are taking here. Deflection would be maximum, will be at the place where bending moment is maximum, right? So it would be near this mid span only. So at mid span the area of steel is 314, the percentage of steel is 0.31. Fs, this it is written very small, so Fs is equal to 0.58 Fy, area of cross section of steel required. So the required area of steel was 300, and what is the amount of steel we provided? We provided 314. So this factor 300 by 314, it comes out to be approximately 1 only, 240 only we can take. Otherwise if we calculate it, actually it is 0.58 Fy steel required by steel provided, it is 230. So it will be slightly below this line, and the percentage of steel is 0.3. So it is, this is 0.2, this is 0.4. So exactly at the center this would be here. So when we move up, we are continuously moving up, and at this point, right? So here, somewhere here it is touching this line, that is 240. Right, so 240 corresponds approximately 1.5. So modification factor for tension reinforcement Kt is 1.5. A quick recap: on the x-axis we have the percentage of steel. Percentage of steel is 0.31. You put a scale. This line is 0.2. This is 0.4. Somewhere in between, slightly towards the right side, and you move up, and you come to this. Fs is equal to 240. So this is the steel that we are using. So it is approximate value is Kt is equal to 1.5. So when we solve this, span by depth is equal to 2600 by 100, and it is less than Kt is 1.5, 20. So 26 is less than 30. So this is check for deflection. It is also found okay. Let's move ahead. Check for development length. Bond and anchorage hand. Development length are very important to maintain the integrity of the RCC structure, especially, right? Then only it is able to take the load. So the bond between steel and concrete is very essential. Unless they act together, right, there is no slippage between the steel and concrete. Effectiveness with which it can bear the load will not be there. So some extra length to provide the full bond between the steel and concrete, we provided as the anchorage length, and the bond failure may be avoided by provision of additional development length. So that is very important. So to have a proper bond and anchorage between the steel and concrete, sufficient length should be provided, and it will result in there won't be any slippage, there will not be any failure, right? So the first aspect is the design bond stress, that we refer to as tau BD. It is defined as the shear force per unit nominal surface area of the reinforcing bar. The stress acts on the interface of the bar and the surrounding concrete along the direction of the bars, parallel to the bars. So if you see the value of tau BD for M20 is 1.2, and for M30 it is 1.5. So as the grade of concrete increases, the value of bond, that is tau BD, bond stress, is also increasing. This value is for the plain bars, and in our case we are using as HYSD 415. So 60% of this value can be increased. So simply multiplying it by 1.6 times 1.2 will get the tau BD value for HYSD bar in tension. Okay, and for bars in compression, this value can be increased by 25% by multiplying 1.25. So here in our case we don't have to multiply with
1.25 since it is a tension steel. So this value is LD required. This value is, again this formula is given in the code, 5 sigma s divided by 4 tau BD. So what is phi? It is the dia of the bar used, and we are using 8 mm dia bar. So this is for main reinforcement only. And what is sigma s? Sigma s is 0.87 Fy. So grade of steel is 415. Simply multiply it with 0.87 Fy. And 4 times tau BD. So for M20 tau BD value is 1.2. So since this value is corresponding to mild steel, for HYSD we need to magnify it or multiply it with 1.6. So LD required would be 376 millimeter. And LD available, that is anchorage value, depends upon M1 upon V plus L0. So what is M1? It is 0.87 Fy. AST, this value again, this is given in the code, right? So towards page 96 this value is given. So 0.87 Fy AST D into, so putting all the values you will get the moment of resistance at support. Make sure that area of steel is half that we provided at the center. So at center we provided 314. So at support the area of steel would be half of it, that is 157. Value of V will be again, we'll keep it as 15 kilonewton as we calculated it. And let us assume that we are providing a 90-degree bend, right? So for 90-degree bend, the value of L0 would be 8 times 5. So the value would be 64. 5 into 8 into 8, 64. So if you put M1 by V into L0, this value is 430, which is greater than 376. So this again, this value is okay from the developmental point of view. So this is the final diagram which we should make, and this is what an engineer is expected to do. These are the structural drawings, and many other similar drawings would be submitted to the contractor and they will execute it, right? So this is eventually the answer would be in this form, the diagrammatic representation of the answer. Thank you.